So I'm going to jump right into it. So last night I was looking at, the interest of reinforcement learning with Google Trends over time, and of course reinforcement learning, as most of us know, has been around for 70 years really, if not more. But just looking from 2010, you can see that when DQN came around, there was quite a shift in terms of interest, and this is not really surprising to many of us if we look at even the Deep RL workshop at one of the NERPs in 2018, I think. Doina gave a talk and she was like, this is a conference, this is no longer a workshop. The number of people interested in this field has really grown dramatically. And it's pretty well coupled with the interest in deep learning. So deep learning, this is probably where ImageNet happened, or around here, the AlexNet, sorry. And so that really spurred this interest in deep learning, and DQN, one of the big parts of it, was the incorporation of neural networks. And so a big part of what has made reinforcement learning such a popular and powerful strategy for learning behaviors and policies is this coupling with neural networks. And this is really, you see this slide often when people give talks about reinforcement learning, about all its success stories. And all of these are using neural networks. So it's really neural networks coupled with RL that have given us these powerful agents to accomplish these very challenging tasks. But again, if we come back over here, it's the reinforcement learning part of it is still building on the decades of reinforcement learning research that many of us have been doing that preceded the use of neural networks. And when starting it from DQN, and still now, although things perhaps are changing a little bit now, the traditional way of introducing a new idea or publishing a paper is, you have some motivation, what you want to do exploration better or something like this. You have some baseline algorithm, so you're going to be epsilon greedy with your new exploration algorithm. Likely you have some theory. You need the mathiness, as it's sometimes called, to get your paper in. But the theory, as the mathematical tools we have, limit us to theory on linear systems, not on neural networks. So we prove things, we prove convergence, we prove upper bounds on error, we prove regret bounds, etc. And then we take this theory and adapt it to be used with neural networks, right? Because this is what is really giving us this expressive power. And then we try it on some benchmark like the ALE, and hopefully show that our line is above the baseline, and then we get our paper in. The challenging thing is when we have this, what we really want to do, it's not, at this point we don't really care about getting good scores in Atari. That's not the point of the benchmark. What we want to be able to do is take these algorithms and these new ideas that we develop and apply them to real world problems, like a robot vacuum cleaner. Mine never works, and it's something that I wish it did work. And it's really hard to do this. It's really hard to take these algorithms and just plug them into these real world problems, even for simulated environments. Your talk earlier today was saying, it took a team of experts to really get RL working in this simulated racing environment, even though, of course, it's very complicated, but it still took a team of people to do it. And part of the issue is that, these neural networks, it's not like a simple thing. They have all these parameters that we have to play with. What's the base algorithm we use, what type of network we use, the optimizer, the size of the replay buffer, then hyperparameters like the batch size, etc. We have to play with all of these things that were tuned specifically to work well. For instance, if you're building on Atari, they were tuned to work well on Atari, but when you go to something different, likely won't work. Sorry, this is not supposed to be there. This is part of the reason is because of what I call the formalism implementation gap, and I'm going to explain in a bit more detail what I mean by this. So I'm just going to keep track of time. So an MDP. This is sort of the first ingredient when we talk about RL. And in most RL papers, we start off with the background section and we define what an MDP is. It's this tuple that has states and actions, etc. And this is what we build a theory on. So it's very useful for doing theoretical work on this, and also for being very specific about what our algorithm is. So we'll take this formalism, this MDP formalism, and we'll define our algorithm with respect to this MDP formalism. That's all fine and great. But of course, we want to benchmark it. We want to test it out and compare it against other algorithms. And so we write an implementation of it. And this, we use Python and use TensorFlow or JAX or PyTorch or something like this. And then we want to test it. Okay, we want to test it on Atari. Okay, so let's test our algorithm on Atari, but as we should all know, one does not simply run on the Atari benchmark. The Atari was an actual console that you have to plug into a CRT TV and, to get it working. To actually run on Atari, we need an onion of layers, wrappers, to be able to do this. So the first thing is the Stella, which I'm sorry if I'm repeating some of the stuff Mike already mentioned, but the Stella was an emulator to emulate the original console. But of course, this was not built for reinforcement learning research. So then Mike and Mark and others built the ALE on top of that to provide this interface for RL research. But again, the ALE was just for the ALE. And then as the field grew, people wanted to use their algorithm kind of seamlessly, go from the ALE to, let's say, Mujoku or ProcGen or whatever. And so then these extra wrappers came around that sort of unified this and provided a unified interface for interacting with not just the ALE, but other environments. And so this is what I mean by the formalism implementation gap. We define our MDP, and the MDP is meant to specify the environment that our agent is interacting with. In this case, it's the Atari games that we're playing. And we have our implementation, which is meant to interact with this. But really, if you think about it, and I'm going to force you to think about it a bit more with all my slides, there is quite a gap there. So we specify things mathematically, but then when we implement them, things start getting a little flakier. And so the first exercise I decided to do is to think of the ALE. OK, what if we really try to map the ALE as an MDP? And it turns out that it more naturally maps to a POMDP, and I'll explain why. Probably most of you know what POMDPs are. If you don't, I'm sorry, but I'll go through this somewhat quickly. It's very similar to an MDP, where we have a set of states. These could be Atari frames, or it can be the cells in a grid world. We have a set of actions, the joystick movements, or up, down, left, right, etc. An initial distribution of states, so whenever you restart an episode or a game where you begin. A reward function that maps states and actions to some numerical value, and this is what you're trying to maximize. Transition function, when you take an action from a state, what's the distribution of next states where you'll end up? And if you stop there, that's an MDP, right? And one nice thing about MDPs is, as the name suggests, the optimal policies are Markovian. So you can find optimal policies that depend only on your current state, and you can ignore everything that came before it, and you can act optimally in that way. POMDPs generalize this a bit more by adding what's called a set of observations. And so the agent will actually no longer see the states, but it'll see observations. So this could be, for instance, just the color of the wall, or the scent around you, or something like this. And you have an observation function that maps the ground MDP states and the action to a distribution over these observations. And these observations are what the agent has to use. And so they might be imperfect. They might be incomplete. So you might not know exactly what state you're in, and that will depend on how expressive the observations that you're receiving are. And one challenging thing here is that optimal policies in POMDPs are not necessarily Markovian. So you might need more than just your current state to be able to act optimally. And so before the days when we use deep nets, often when we think about theory, we talk about belief states, which are distribution over these underlying states. And of course, this assumes that you can enumerate all the states and you have access to them beforehand. But another way you can deal with it is just using histories of observations. And people do this with LSTMs or even transformers. And that can help deal with some of this partial observability that you have with POMDPs. OK, so now that you're all expert in POMDPs, let's map the ALE onto a POMDP and how that would work. So first of all, what are states? So are the frames in the game the state? Is this the state? No. And partly because of all this onion of wrappers that we use here. So one of the aspects that Mike may have mentioned is this idea of frame skipping. So when we talk about MDPs, we always say, the agent is in some state, takes an action A0, and then lands in some new state X0, then selects a new action A1, lands in X1, and continues this. So for every state, the agent picks an action. What the ALE does is it says when the agent picks, let's say, action A0, it's going to go to state X0, but then it's going to repeat that action a number of times, and the default is 4. So the agent is not selecting an action at every new frame. It's selecting it every 4 frames by default. And things get more complicated because it's not like the agent gets to see all the 4 frames. The agent really is only, we're getting only a max pool of the last 2 frames that we saw, right? And it's more complicated than that because then we also have this thing called frame stacking, where we take these max pools that we get, and we're going to stack, by default, 4 of them. And that's what we send to the agent. So rather than the agent getting this frame, which is the simple, this would be the simplest way of defining a state in an Atari game, the agent's getting this weird thing where it's a stacking of max pools of the last 2 frames in this set of repeated actions, and that's what's sent into the agent. And this is the default that pretty much everyone is using if you use the ALE with any of these wrappers. And so I decided to play around with these and see the impact of that. And I was talking to Mike about this, and he predicted, he's like, with frame skip 1, it doesn't work. And this is the blue line here. And you can see that even if you try different stack sizes, when you have a frame skip of 1, the agent's unable to learn at all. And the important thing here is that the choice you make of this frame skip has a big impact on the resulting performance of the agents. And so this might seem like just a technicality, some detail, some unimportant detail. But if we really want to be specific about this formalism implementation mapping, we need to be really explicit about this. And I think we need to understand better why this has such a big impact. Well, time is flying, so I'm going to go really quickly. Actions. So the ALE has this idea of full or minimal action sets. So for a game like Breakout, you can move the joystick in all sorts of directions, but really in Breakout, the only thing that you can do is left or right. So the ALE allows you to train with minimal actions, which is just the actions that have an impact on the agent. And this, of course, makes things easier, as one would expect. If you add the full actions, in many games, performance degrades quite a lot. Again, not just a technical detail. This is really important for specifying this formalism implementation mapping. I'll just skip through this quickly, but the initial state distribution, again, because Atari games are deterministic, in the original work they found that they could find open loop policies, which means that they can just pre-specify the policy from the beginning and win the game, because everything is deterministic. And if you start deterministically, that's what works. When humans play, it doesn't matter because we're less deterministic. And so in the DQM paper, they added this no-op, these random no-ops at the beginning to make it harder for agents and more interesting. Again, this is part of this mapping that I'm mentioning. Reward function. Each game has its own distribution of rewards. Some games go from 0 to 100. Some games go from 0 to 10,000. And so what DQN did is they clipped the rewards. So they decided we're going to clip the rewards between -1 and 1. This makes it easier to have global hyperparameters for your network, but it does introduce reward aliasing, and it can have an impact on performance. The transition function. And this comes back to the question of what are your states. So how you define the transition function depends on what your states are. And these wrappers can also affect transitions quite dramatically. For instance, when you're playing an Atari game, there's this notion of lives. If you played any video game, you have like 3 lives, and so you can continue from whatever life. Sometimes you spawn where you left off. Sometimes you spawn at the beginning. And then there's this parameter that allows you to start a new episode every time your life ends. And this has a big impact in terms of how you do, for instance, the Bellman backup. So if you terminate an episode there, then you're no longer backing up past that end of life episode transition. And again, if you just flip this simple parameter, you can get very different performance in different games. And it's part of this formalism implementation mapping. So the first recommendation from this talk is that I think we should really try to be a lot more explicit about the formalism, about this gap that I mentioned, not just for Atari games, but in general. I think when we're trying to be well-founded in terms of the theory, it's important that we can't prove things about deep nets for the most part, but let's at least try to maintain that connection with the theory that we're using to motivate our algorithms. There's a couple of other recommendations that I'm going to go through fairly quickly. So something like discount factor. There are algorithms that use varying discount factors or use multiple discount factors, but we're often evaluate things with a different discount factor. In the ALE, for instance, we actually, all the plots that you see for ALE, these are non-discounted plots. So when we're evaluating the agents, we're getting rid of gamma. And this is important, an important thing to specify, and in particular because different choices of the discount factor when you're training will have very different outcomes for different games. So these are just 3 different values of the discount factor, and you can see that you can pretty much choose any ranking, and there's a game that has that ranking. So this is something that's important to understand, and this is something we explored in a paper that we presented at RLC last year. The other thing that's important here is to be explicit about the experiment length. So we have the 100K benchmark, and then there's the standard 200 million. Some people use less just because 200 million is quite expensive to train. And that's fine, but I think the important question here is, why are you running for that length, right? If you're really going for sample efficiency, okay, sure, 100K is good. If you're not, then why are you picking the length that you're picking? And see if you can try to run your algorithm for longer and make sure it doesn't collapse. Just to exemplify this, if you were to try to do some hyperparameter optimization, I think this is learning rate. If you did it with 100K, you would find that this green one, for both Dr. Q and DER, it's one of the worst. But if you let it train for longer, it ends up being the best. So these types of decisions of how you do the hyperparameter tuning and how you're evaluating your algorithms in terms of length is very important. And this is something that's explored quite nicely in this paper that was published at JMLR and presented at ICML recently. There's a QR code if anybody wants to check it out. Next recommendation is you need to be very explicit about what you're optimizing your hyperparameters on, so what set of games and what set of games you're evaluating. Just as an example or as an exercise, this is a pop quiz. So I'm comparing DQN in blue against rainbow in orange. Which one of these 3 plots is the correct plot? Okay, raise your hand if you think it's the first one. Raise your hand if you think it's the second one. Raise your hand if you think it's the third one. Okay, most abstained. I'd say the majority picked the third one, but they're all correct. So they're just picking different sets of games. What I was showing at the beginning, this was an aggregate performance, which is what most papers actually end up doing. They show these aggregate performance curves and hopefully show that their algorithm is better than the baseline. But you can basically, DQN and Rainbow, you can pick 5 different games and you get kind of whatever result you want from this. And of course, I'm cherry picking these games, but it's just to highlight the importance of really being careful with how you evaluate, careful and scientifically rigorous with how you choose what games to present the final results on. And I'm going to come back to this in a little bit, actually right now, because one of the main recommendations that I'm hoping you take away from this talk is that we need to stop focusing on these aggregate performance metrics like we have here, even though these IQM plots came from a paper that I was an author on. But I think, again, similar to what Mike was saying with over-indexing on score maximization and Atari, I think we're starting to over-index a bit on these aggregate performance curves. And as we see here, like it depends on what games you choose, you can kind of get whatever aggregate results you want. What's interesting is for me, what's interesting is why is Rainbow so good on these and so bad on these other games? Like, what is it about these games that makes one algorithm perform better than another? And we can see this, not just with Rainbow and DQN. If we look at these 4 games and we're comparing a whole bunch of different algorithms, you can kind of get all the orderings you want. So some algorithms are much better than others, and why? This is not something that I don't think we really understand as a field, and I think it'd be important. Because it's, as you're doing hyperparameter tuning, and again, coming back to the original motivation of running this on something other than Atari, how are you going to pick the batch size, for instance? So here I'm evaluating 4 different batch sizes with Dr. Q, and you can see that the ordering of the values are completely flipped on these 2 games. So which one is the one that you should, if you're going to take this to a new game, which one are you going to pick in this case? So from all of these results, for me, the thing that comes out is if we can't get our agents to work reliably on all these games, on these Atari games, which people say Atari is no longer interesting, it's boring, etc. But if we can't even get them working reliably there, what hope do we have for real-world complex systems where we can't just run all sorts of experiments and simulation and pre-tune our hyperparameters? And a related question is, when can we trust these benchmark results? So we have all these Atari results, all these papers using Atari results. And I understand why people are starting to get fed up with it. And thinking, why are we still running these experiments? And I think the more general question is, how can we develop a sense of trust in the results we get from the benchmarks? And the recommendations that I was mentioning before, I would argue are meant to try to increase the trust that we get from both the papers and the science that we publish, but also from the benchmarks. And so thinking about benchmarks, I was thinking to myself, what does it mean for a benchmark to be meaningful? It's not just, a benchmark's not just there so that you can get your paper published. A benchmark's there so that we can get a better understanding of the algorithms that we're building and the understanding that we have of these algorithms, so that then we can more reliably deploy them in real-world systems. And so the last part of the talk, I'll be focusing on what I think makes a good benchmark and why I think the ALE is still a good benchmark for doing reinforcement learning research. So one of the things that I think is important for benchmarks is that they're well understood. And the reason for this is if you've reviewed for conferences, you've probably seen all sorts of different new environments and new benchmarks that come out, and that's fine. But it's very rare for some of these new environments to really get picked up by the community. And the reason for this is that as a reviewer, if I have to evaluate these plots on some new random environment that I've never seen before, I don't really have a frame of reference for, is this good, is this bad, is this challenging, is this obvious? So give me some Atari results, and that I know how to handle that. And so from the academic perspective, I think there is a lot of use in having these well understood benchmarks. The diversity, I think, is important because, again, Atari games are quite diverse. So this is just to show that the ALE, we should all know by now, is quite well understood and well used. But that diversity, I think, is quite important because we're not just training on cartpole. You were talking about cartpole today. That's a single environment. Whatever agent you trained on cartpole is unlikely to work, let's say, on Acrobat or mountain cart. You're talking about not cartpole or cartpole. The nice thing about Atari, even though, as Julie mentioned earlier, we're training a network per game, it still gives us a very diverse set of games that we can train on and evaluate, especially if we stop focusing on these aggregate results and look at really the per game differences and when things work and when things don't. The other thing that I think is important about the Atari is that it was not designed for RL researchers. So again, there's other environments that have come up that were designed by RL researchers for RL researchers. And so there's a naturally experimenter bias, right? So if I want to design a benchmark for doing exploration, then of course I'm going to be focusing on this type of exploration. If I have an algorithm already in mind, maybe subconsciously I'm making it a bit easier for my algorithm, or it's designed for that algorithm. Atari games were designed for people to play in front of their TVs. And that, I think, removes that experimenter bias, which is quite important. The other neat thing about Atari games is that they have different modes. So you can think of this as difficulty levels for the different environments. And this paper, Jesse Fairbrother published a paper on this a few years ago, not the one I'm mentioning here. And they showed basically most of the algorithms are terrible at generalizing for these different modes. So for instance, it's not here, but in Freeway, which is this game where you have to have a frog that crosses the street, and there's cars that move back and forth. Just increasing the speed of the cars, that's it. An agent trained in the original mode will totally collapse in the new mode. And so as humans, we see that as, that's stupid. Like, I know how to play. If I learn in the one mode, I can generalize to the other one. And so I think this is quite interesting because we already have this platform and we already have this familiarity with these games. But yet there's this generalization threshold that we still haven't overcome. There's lots of, as long as we're explicit about this formalism gap, I think there's lots of ways we can play with the environment based on what type of question we're trying to answer. So deterministic versus stochastic actions, or as they're known in the ALE, sticky actions. This allows us to add an extra level of complexity and non-determinacy to our environments. Last year, we added continuous support for continuous actions to the ALE, which was something kind of interesting because if you think of when you're playing with this joystick as a human, this is a continuous thing, right? Even though it has discrete actuators underneath, we're really moving a continuous object. And so it was kind of surprising to me that nobody had thought of this yet, but now there is support for continuous actions, and things are much harder there. So if you hear Atari games are easy and now we have agents to do it, turn on continuous mode because it'll make things a lot harder. And another thing that I think is quite important, and I sort of hinted at this already, is having benchmarks that are naturally extendable. So if we already solved Atari and it's uninteresting, well, now we have these continuous actions. And there's a bunch of other follow-up papers that have built on sort of the Atari foundation, have added different supports like multiplayer or GPU accelerated emulation, some cheaper versions of Atari like Minotaur that's based on Atari and allows you to run experiments in a lot faster and without as much compute requirements. But again, the important thing here is that we're not trying to just win and get our paper published. Why we're all here is because we're interested in the science of reinforcement learning and we want to advance the algorithms that we build in reinforcement learning. And so all of the choices that you make, whether you're using sticky versus stochastic actions or the different modes or one of the cheaper versions of Atari, they have to be in service of the scientific question you're asking. And so this comes back to this question of being very specific about what environments you use to optimize your hyperparameters on and which ones you use to evaluate, and all the recommendations I mentioned before. Because the point of Atari, I mean, maybe originally when DeepMind was working on it in the early 2010s, there was more about winning because they wanted to demonstrate that RL could achieve superhuman capacity. I think we've passed that point now. We know we can do this. So if that's what you're trying to do with Atari, then sure, Atari's over. But I think the benchmark itself still stands as a really useful benchmark, an evaluation platform for advancing the science of RL. So forget about winning or losing. It's really developing this understanding. I don't know if Mike mentioned this in his talk. I unfortunately wasn't able to see it. But this book, if you're interested in the history of Atari, the console, is fascinating. I love this book. And you really get a sense of some of the challenges and the obstacles that the developers had to overcome to develop Atari and why Atari is the way it is now. There's a lot of peculiarities we see with Atari, with some of the games, if you've ever played them or seen some of the videos, that are really linked to the time when Atari was developed, the technology that was available to render these graphics. So really fascinating read if you want to check it out. And with that, I'll end and I'll leave you with some references that I think are related to this notion of really advancing the science of RL, not just winning or losing, but playing the game. And by the game, I mean not the Atari game. I mean the game of reinforcement learning research. And so all of these papers are excellent. I encourage you to read them. My website's there, and my socials on Twitter and Blue Sky are there. And happy to answer any questions if we have time.
So I've always wondered with Atari, because the original Atari console was so limited, and they had to do all of these tricks to get anything to work. I wonder if that is a big inductive bias in terms of what kinds of things happen in games. So I kind of worry about overfitting to RL techniques that work specifically in the kinds of games that can be implemented using these tricks that you can do on this particular 1970s hardware?
Yeah, that's a great question. I think, so one point, and maybe I should have made this clear, the free Zoom meeting has ended. The point I'm trying to make is not Atari is the only benchmark we should be using. I think it's one of many different benchmarks that we could be using. And again, it comes back to the question of what's the scientific question you're trying to answer. So a lot of my recent papers have been focused on Atari, not because we want to win at Atari, but because it's something that we understand quite well. And so there are still a lot of interesting scientific questions that are somewhat agnostic to whether we're running on Atari or not, like for instance, plasticity loss or the types of architectures you use, or how well gradients are able to traverse through your network when you have these high levels of non-stationarity. And I think those types of questions, you can kind of choose whatever benchmark you want. I don't think they're really overfitting to this particular inductive bias, which I agree is there. I think perhaps some other questions, like for instance, exploration. I think for a while the community was over-indexing on Montezuma's Revenge. Everybody wanted to win Montezuma's Revenge. And so you'd have papers that were published and got really good scores on Montezuma's, but then when you try them on some of the non-hard exploration games, they don't do as well. That again is not really related to the inductive bias, but the strategies that they were of Atari in general, but the strategies that they were coming up with were quite overfit to this. So I think it is a general problem in not just for Atari, but with any type of benchmark or environment, that whatever strategy you or algorithm you come up with is not overly indexed to that. And so again, coming back to the idea of the diversity, I showed a bunch of plots where you see results sometimes doing well, sometimes doing poorly. And I think that's the interesting question. And maintaining that diversity, I think, is what's important. And maybe helps mitigate some of that inductive bias.
Thanks.
Thank you. We'll just have maybe one or two more questions.
Yeah, sure. So I really like how you frame this as a POMDP first, because I feel like that is, like most things are, at best POMDPs, they're probably actually much worse than that. Mm-hmm. But we don't really, when people do Atari, we just don't treat it that way. We often don't have RNNs. There has been work that uses RNNs in them, and that's like the bare minimum to try and handle a POMDP. So what could we do to Atari to kind of make people see it through that lens and really tackle those kinds of problems?
I think really tackling head on this formalism implementation gap is an important thing. So the types of works I've seen using RNNs and that type of thing, it was still in the time when we were pushing for higher scores and pushing for performance results on these agents. And that's fine, but it's sort of taking this, whatever the ALE is at the time, whatever the default parameters are at the time, which includes all this frame stacking, skipping, and all this stuff, and that's just part of it. So it's POMDP, but we haven't really been very specific about that. So if you want to explore, adding LSTMs or adding some type of mechanism for dealing with history, then I think for me, the way I would approach it is, okay, we have this parameter that we know affects the partial observability, like the frame stacking and the max pooling and the frame skipping and these types of things. Let's play around with this, and now let's try to understand how, when we make it more or less partially observable, that affects the performance of whatever we're proposing. So it becomes not a question of using the default settings, can we get the highest line? Right. It's more, this is an algorithm, and under all these different settings, this is how it performs. So that gives us more confidence that if we go to a different setting, which is still maybe a POMDP, we have a better understanding. If we understand the environment a little bit, then we say, okay, maybe it's more akin to this. And that might, I think that connects to some of the frustrations that you were mentioning with choosing the end steps or some of the other design decisions that you had to make. At the point, of course, you were still working to get the algorithm to work well.
Right.
But then once you've passed that point, then I think it's interesting to think of, okay, so now what's, how do we make this generalized?
Thanks.
I think we're running late for the panel, so please feel free to reach out to Pablo later.